Yes, yes. Okay, so good afternoon, everybody. Today, and welcome to this week's seminar in the GCS program. We have, as usual, two talks, but this week we have also a cake in a break. So we have to go back to the other building for the cake. The first speaker, I should also say that the talks are somewhat related, and the first one is both the speakers are from the University of Kent, by the way, and the first one is Peter Hydon, who is going to talk about conservation laws and Euler operators. Please, Peter.
Thanks, Brynjolf. Okay, so yes, as Brynjolf said, our talks are related. I'm not going to talk about anything numerical, but what I have to say is, if you like, related to the background of the project that Gianluca Frascaccia and I have been doing, which he will tell you about in his talk. Okay, so conservation laws. Most people are extremely familiar with conservation laws. I'll spell out a bit of standard notation and introduce the Euler operators, which are the familiar things that you get in Euler branch equations. And then, after a brief review of that and some of the things that Euler operators are useful for that people don't often think about, perhaps, I want to focus in on a question that really is at the heart of symbolic calculation of conservation laws. So Gianluca and I are working on trying to develop efficient symbolic means to construct bespoke finite difference methods that will preserve conservation laws. And it's one thing being able to do calculations by hand for simple things, but you want to try to be able to automate the process as far as possible. And so there's a key question in this, which is how do you invert the divergence operator symbolically? And we'll look at that for the second half of the talk. Okay, so what is a conservation law? Basically, if I've given a system of differential equations, A is 0, there may be L of them, then a conservation law is a divergence expression that is 0 on all solutions of the differential equation. So it's something that applies right across the board on the whole solution manifold. To fill you in on the notation, I'm using here d by the total derivative with respect to xi. And so total derivative is like a partial derivative that treats dependent variables and their derivatives as if they were functions of x. Okay. So it's just the analog of div. And the functions fi are the components of the conservation law. And I will always use the Einstein summation convention. I don't know how to big signals. Okay. I'm also going to make one key assumption that is crucial in the formal theory of differential equations, which is that everything is as nice as it needs to be. In particular, locally, we're looking in regions where functions are smooth and where they depend on a finite number of variables. So I'm immediately sweeping away a host of potential complications. So conservation laws come in equivalence classes. And first of all, you have to say what's in the class. And the zero class consists of the trivial conservation laws. These are ones of two types. There are trivial conservation laws where the components of the conservation law are 0 on solutions. And so, of course, the conservation law will be satisfied on solutions if its components are 0 on solutions. That doesn't really tell you very much. The other sort is the sort of triviality where divergence is 0 whether or not you're looking at solutions of the differential equation. In other words, if in 3 dimensions, for instance, f was a total curve, there's a convention that we write capital letters for total things to distinguish them from lower case for an ordinary curve. So a conservation law is trivial if and only if it's a linear superposition of the above two types of triviality. And then that is an equivalence relation on the set of conservation laws. It's a vector space of conservation laws. And two conservation laws are equivalent if their difference is a trivial conservation law. So the key question then is, how do you identify the various different equivalence classes of conservation laws? Now this is really important for numerics because conservation laws have a rather deep origin as cohomology classes of something called the restrictive variational bicomplex, which essentially reflects the topology of the solution manifold. So these conservation classes, if cohomology classes, if you think of cohomology as if you like giving instructions to certain things, well, the solution can't do what it's like. It likes, it has to satisfy each of those conservation laws. Those are the instructions. So we want to find those things, and ideally, in finite difference methods or finite element methods, try to preserve those. Okay. And there is a simple way of finding these equivalent classes. Each one has a characteristic, and you can find a characteristic of a conservation law essentially by integrating by parts to get an equivalent conservation law in the form where each component of your equation, each equation in your system, if you like, is multiplied by a function, and the output is a divergence. Now clearly, this div f tilde is a conservation law because it vanishes on solutions A is 0. Okay? So it is a conservation law, and the two are equivalent if f minus f tilde is trivial components. Okay. So every conservation law is equivalent to one in this so-called characteristic form, and it's just, as I said, integration by parts that proves that. Okay, here's a little example. I won't do too many of this sort of thing, but I thought it's nice to see it. KDB, the third conservation law, if you write it out, C is this operator acting on A. It's a scalar equation, so there's only one component. Okay, you integrate by parts, and you can decompose that conservation law C into two parts. This part, which is in characteristic form, a function times A, plus a divergence, in this case just one component, that is trivial because the component is 0 on A is 0. Okay, so there our characteristic is that function Q in red, and this extra bit is trivial. So that's how you find characteristics. And Alonso has a theorem. It wasn't in Peter Robert's first edition of his yellow book, but it is in the second edition, which says that if A is 0 is in Cauchy-Krylov skyfall, that's an if, not an only if. It does apply more generally. Equivalent characteristics correspond to equivalent conservation laws. Okay. So, on to Euler operators. As I said, this is a quick run through of the basic theory before we get into something a little more meaty. But if we think about scalar equations with one independent variable, the Euler operator is the standard operator. Here I'm using the notation uj for the jth derivative of u with respect to x. And that's of course the same as the jth iterative, this total derivative acting on u. Okay, so if we go back to here, we have Euler operator is the adjoint of dx to the j times the partial derivative acting on whatever. And that adjoint for the differential operator just takes every derivative in places where it's negative. So that's nice and easy. For expressions, yeah, so the Euler Lagrange equation is EU of L is 0 for Lagrangian L. If you've got more variables, then it's really helpful to try to tidy up the notation with a multi-index. And so a multi-index has a label, one value for each of the independent variables, telling you how many times you're differentiating with respect to that variable. Okay? And so dj here is the number of derivatives labeled by that multi-index, and its adjoint is minus dj, which is the same thing but with all the d's replaced by minus d's. Okay. Okay, so you stop me if you find anything confusing, but I think it's straightforward at the moment. So the standard Euler operator with respect to a dependent variable u alpha is EU alpha, and it's the derivative with respect to u alpha j, and I done that by the adjoint of dj, u alpha j here being the djth derivative of u alpha. Okay. And that gives you that expression. So your Euler Lagrange equations would be EU alpha of L, if L was a Lagrangian, for each alpha, each dependent variable u alpha. Okay. So now I want to, that's just a reminder, now I want to go a little bit into the connection between Euler operators and conservation laws. Euler operators kill all divergences. That is to say, the application of an Euler operator to a divergence gives you 0, and something is a divergence locally if and only if it is in the kernel of all of the Euler operators, one for each dependent variable in the expression. And so that's a nice little lemma. There's a corollary to this, which is, I think, one of the simplest yet nicest things that people don't very often know about, and it's this. If you've got a conservation law with a characteristic Q, with components QL, okay, and if that conservation law depends on arbitrary functions of x, and in particular, because the equation is fixed, it's actually the characteristic that depends on those arbitrary functions, G. Sorry, it's one arbitrary function in this corollary. You might involve its derivatives, and that is true if and only if there is one differential relation between the functions that make up a system of equations. Okay, and all you have to do is apply the Euler operator, not with respect to any of the u's, but with respect to g, this arbitrary function, to the conservation law. Now, this is a generalization of something that Liz Mansfield and I used in a proof of Noether's second theorem that's considerably simpler than the existing proof, and also enabled us to develop a Noether's 1.5 theorem, which covers all the intermediate cases. And here we've got just a little statement that this adapts easily to multiple arbitrary functions, and it also allows us to deal with functions with constraints. And for Noether's theorem, that's a bridging between Noether's first theorem and Noether's second theorem. At one extreme, where the arbitrary functions are only arbitrary constants, so fully constrained, you get Noether's first theorem. At the other extent, you get Noether's second theorem, where there are no constraints at all in the G. However,
sorry, can you explain for the ones that we don't know anything about these things, what is Noether's first theorem and Noether's second theorem?
Okay, so Noether's first theorem is that, suppose I have a symmetry. Pushed a bit harder. So a symmetry generator in vertical form or the evolutionary form is something. Now I'm going to use Q here for a good reason, but let's have full generality. Going for the of x plus and so on. So this can be written as dj of q alpha times partial to e under j. Okay. Something is said to be symmetry generator, and this may be a generalized symmetry generator, so those Q's might depend not just on X and U, but on derivatives of U as well. Okay. For a Lagrangian, so if we have a Lagrangian functional L is L dx, then it's a variational symmetry if, when you apply that operator X to this function inside, you get a divergence. Okay? That's just said to be a variational symmetry generator. The reason is, of course, what I got to say is this generator is what you get when you vary U by a small amount, okay, an infinitesimal amount. And these are the components that you get. So under those circumstances, you've got this generator XL being a divergence. And remember, you've got something like this, DJ Q alpha for X. Then we've got DL, du alpha J is div T. Okay? Follow me so far. Brilliant. Integrate by parts. When you integrate by parts, this dj goes across and becomes its adjoint, and so you get the extra bits you get can be piled into that divergence. Okay, and we can add those on as part of the divergence. So then you get Q, the adjoint of dj. Applied to the L U alpha J is its divergence of something else. It's called P tilde. Okay. So each Q that corresponds to a symmetry generator turns out to be a conservation law for the Euler-Lagrange equations. Sorry, I missed out the alphabet, because that is precisely EU alpha of L. So maybe I should have called my P tilde F to line up with the other notation. That is Noether's first theorem. Noether's second theorem says if you have some of these variational symmetries that depend on arbitrary functions, G, for instance, where it's a completely arbitrary function of the independent variables, X, then there is a differential relationship between the equations, between your Euler-Lagrange equations. This is used in gauge theory. It's the basics of gauge symmetries. There's a whole train of intermediate cases, which Liz and I looked at, where essentially you have dependence on functions that are not completely arbitrary, but are arbitrary in some respect. They might depend on one independent variable rather than all of them. And you can deal with those too, and I'll show you how in the next slide. Now, I ought to say that that on the board here, I was dealing with Q's that generate symmetries. However, every conservation law has a characteristic, whether or not it's related to symmetries. Okay, and for non-variational problems, symmetries and conservation laws are not directly related. So the generalization that is in this result is that my Q here is not the characteristic of a symmetry, not the Q in a symmetry, it's the Q in a conservation law. That's the only generalization, everything else goes through before. Okay. So here's a little example. Navier-Stokes equations in velocity vorticity form. So the pressure is eliminated by taking a curl. And you've got three equations here. For 6 unknowns, this is R3, and we have the 3 components of U and the 3 components of omega. Okay, that ought to make you suspicious. 7 equations for 6 unknowns. All right, but let's plow on. This system has a conservation law where there isn't one arbitrary function, g, of the spatial variable x in time. Okay? And that's the conservation law. It's in a paper by Chevikov and Overlap, 2014 is when fluid mechanics. Now, that conservation law, if you actually write it out and then put it into characteristic form, that's the equivalent characteristic form. Okay, so you've got something times AT and something times A omega. And because A omega and AT are vectors, okay, there's a dot product in there. Notice AU is not involved at all. Okay, but it is a conservation law for all G. Okay, so we apply the algorithm, very simple. Take the Euler operator with respect to G of this, and bear in mind A doesn't depend on G at all, and so that grad just pops over to the A, and this one pops over here, and the time derivative as well, and we end up with a differential relation between the components of AT and the components of A omega. Okay, and that one relation reflects the level of redundancy in the system. Okay. So that is, if you like, a non-variational analog of Noether's second theorem. What about the intermediate cases? And again, I'll just do one example. There's an equation called the KZ equation. A here is up here, that's the equation, and there's a characteristic that depends on an arbitrary function of t, and also on x, and also on y, but in an explicit way. Okay, not arbitrary. So, if we apply the algorithm, now if we were doing it with g an entirely arbitrary function, we would just have q times a. However, we want to treat g as if it was an arbitrary function, and therefore we'll turn this dash, this derivative of g into a dt, and we'll specify, using Lagrange multipliers, that dx of g and dy of g have to be 0. Those are the constraints built in. And so we treat g as a free variable using this variational approach, and apply the operator, and you get something out here. Now, this tells us something nice. We have a new conservation law which doesn't have a dt component. It's this one. Okay. Now, we've got to actually invert this and find out what the mu1 and mu2 are. So inverting divergences turns out to be important. Okay, but suppose we can do that. We have a conservation law. And indeed, because these things don't involve a t derivative, we can multiply our arbitrary function of t back again, and that gives us our family of conservation laws that are equivalent to the original one. Okay.
We are in the whole space.
Sorry?
We are in the whole space.
Yes. Yes.
So no boundary conditions.
No boundary conditions. No, it's all local. All local. Okay. So the key thing here is to invert the conservation law. To find the conservation law components, you have to be able to invert div, and we have to have a routine for doing this. Now, the obvious thing, the small expression, is to integrate by parts, and just to do it by eye. And indeed, Peterov, in his yellow book, recommends doing that, because he gives a formula that will do it for you, and the formula is horrible. Okay. So this is how not to invert div. Okay. How not to invert div is to use that formula which integrates in all directions at once. He did say it was the most complicated formula in the book, and it is. Here's a little example. Benjamin Bohn-Mahoney equation, or the regularized long-wave equation. A is ut minus ux minus u double xt. Here's a characteristic for a conservation law, and if we do this standard symbolic algorithm on it, took ages to do because I did it by hand and not having the software. And the first few terms are these. In fact, this should tell you that something's wrong, because here we've got C is an expression with, okay, 2 derivatives there, 3 derivatives there, and yet we're getting expressions with 4 derivatives. Okay, that's what the formula produces. And that's what standard algorithms for integrating, for inverting div use. And it's the real problem, because this expression swell that is generated when you try and do these computations basically gets them stuck. Willie Herman gave a very nice talk at Lumini last year on this, and basically was saying it would be nice if there were a better method for doing this. And Liz and I, when we worked on a variation complex for difference equations, and found that the natural homotopy operator for difference equations uses integration along edges rather than in a star-shaped domain to the middle, which is what the standard operator uses. So wouldn't it be nice if there was some sort of approach like that that we could use? Well, there is now, and I've worked on that, basically been working on it since I arrived here. Okay, if you did integration by parts, you don't get 17 terms, which is what we get here, you get 5 when you expand that bracket. So surely there's a more efficient way to do it, and that's what I want to talk about.
Yeah, but both results are correct, right?
Yes.
You
Oh, yes.
should be able to form one into the other. So
Yes,
this would work by
You add a curl, div of a curl, and you get the other one. Yes, you can. But the point is, if you're trying to construct a symbolic means of doing it, actually trying to work out which curl to add is really difficult, particularly if the one that you've got to add doesn't actually occur in the thing that you're starting with. Willie and a student of his, Douglas Poole, trying to eliminate curl terms, but they could only do it with what was there in front of them. They couldn't actually sort of create new terms, and that's what's needed sometimes to get the optimal expression. So what we need is an algorithm that produces such minimal representations. Okay, so now I need to introduce partial Euler operators. And a partial Euler operator is essentially an Euler operator, except that you only treat one independent variable as being the independent variable. All the others are regarded as temporarily other variables, which label the derivatives. Okay, so let's just have a look. I'm going to take my first variable, and all the other ones I'm going to index by I, which is a Martin index. So before I had J, which was J1, J2, J3, all the way up to JP. Now my I is going to be J2 to JP, and I'm going to have X as J1. Okay. So I'm going to change my notation. Instead of using UJ, I'm going to use it, if this is the jth derivative of ui, I'm going to use ui comma j. So what's after the comma tells you the number of x derivatives there are. Okay, and all the other variables are treated independently. So each ui is treated as distinct from the others. Okay, then the partial Euler operator with respect to x and ui is this operator. Now it looks like the Euler operator for an ordinary differential equation, in the sense there's only one direction which you're differentiating, the x direction, and ui is the thing, the basic variable we're differentiating with respect to, and then its x derivatives. An important identity here links the standard Euler operator and the partial Euler operators. EU is the adjoint of the di applied to EUIX, summed over y. Okay, remember the summation conventions we was applying in this talk. Okay, so there's the link. Now, one other operator I need, but I won't go into too much detail about it, and that is the partial scaling. So if I've got my UIs being regarded as separate variables, subject only to x derivatives, my partial scaling treats the same thing. So it basically says, I take my function, and anytime I see an x derivative of ui, and that may include ui itself, I replace it by lambda times that. But I ignore the other terms, treat them as if they were constants. Okay, that's my partial scaling rather than full scaling. Now, in the case that f is a differential polynomial, what will happen then is that if I set lambda to be 0, that map projects out all the terms that depend on ui and its x derivatives, but leaves all the other terms there. F doesn't have to be a differential polynomial, but if it is, which is very common in this case, then that's what happens. Okay, so 2 lemmas. The first one, a couple of simple things. The projections commute with the total derivative with respect to x. Projection with respect to ui and x commutes with that. And the kernel of this Euler operator with respect to ui and x consists of the vector space sum of the image of dx and the image of this projection. Now, let me unpack that a little bit. What this is saying is that anything that EUIX annihilates is going to be, possibly, an x derivative, a total x derivative, possibly something that doesn't involve the variables ui or their derivative. Okay. And of course you can have an invert there. The second lemma, the first one is, the first part of this lemma, it comes in 2 parts, is just a restatement of that identity I wrote on the previous page, linking the standard Euler operator with this one. And that is, if I apply the Euler operator C to a divergence, I get 0. I can rewrite that as EUX applied to C is everything else that turns up in the standard Euler operator. So it's the sum over all I, it's non-zero of those things. And because every one of them involves at least one derivative with respect to a variable that isn't x, I can write that as a sum of variables di, pi. Okay. Where pi I have to work out from here. The second part of the lemma states that, having worked this out, there exist functions f such that my di, pi for each I, no sum here, can be expressed as EUX of di fi for some functions fi. Those are good. Okay. What that means is, because I've got EUIX of C being equal to a sum of things in the image of EUIX, I can strip off the EUIX, leaving only the kernel. And what that means is C minus those things that I found, the F's, belongs to the kernel. And we know what the kernel is from lemma 1. It's the image of dx and the bits that are projected out. Okay, so we can construct those solutions symbolically. Now, I thought of showing you the formula for doing this and decided it wasn't a good idea. It's arm-crossing. So, but they can. And there's a unique solution whenever you've, there isn't a unique solution for the f necessarily, but there are solutions that can be constructed symbolically. And you use partial scalings to do that. Once you've done that, because what's left is in the kernel of the Euler operator, there's an mdx component, and you can find that, and the solution is unique. And again, you use partial scalings. Okay. So the uncertainty in this is actually inverting the Euler operator, finding these solutions. There can be more than one. Okay. However, this is enough to get an algorithm. Okay. And the algorithm goes as follows. You're given a divergence expression C. Okay. First of all, decide which independent variables you want to get rid of first. So typically I would take x to be the highest, the derivatives that occur most highly in the equation. And I would run that way. There are rankings where you need to do it in a different way. But it's quite a simple way to rank the variables. Once you've ranked the independent variables, rank the dependent variables, and always in this x and u will denote the first ranked variable. Now there are rules about rankings, but I won't go into those. You start off by letting C0 be C and setting the f's to 0. And what we're going to do is transfer stuff from C0 into f at each stage until we run out of things in C0. Okay. So, now we get going. For as long as C0 contains x derivatives, do the following. Use lemma 2 to write C0 as something plus those extra bits that we found by using lemma 2. Okay, by that inversion. Now remember, those bits are not necessarily unique, but they can be found. Okay. Then project out the bits that don't involve u, or x derivatives of u, and we know that that must belong to the image of dx, because we got rid of the other part of the kernel. Find that, and you get that uniquely using these partial scalings. So now we update. We have found an fi naught for each I. And so we're going to let f be replaced by fi by fi plus fi naught. Sorry, tripping over my fi's. And then all we've got left of our C naught that we started with are the parts that don't contain u or x derivatives of u. And so that becomes our new C naught. And then we iterate. Okay? And then you choose the next ranked UI to replace u, go back again. Okay. So for as long as C0, if you ever get to the point where C0 is 0, then stop. Obviously it branches out of that one and that one. Otherwise, when you've run out of x derivatives, move on to your next variable and do the whole thing again. Okay, and that will give you any remaining terms. Now, what I wanted to do is to, and the other thing to say is you do have to start again with the u's. You know, but of course you freshly rank them when you have a small number of dependent variables, independent variables. So the ranking is inherited from the original parent ranking. Okay. So I want to do a worked example because I don't think you'll believe me unless you see me do it. I have a feeling I need to switch this over. It's good if you don't have hands. Okay, so I'm going to do that BBM equation. So I started with C is, what was it, 2uxt plus squared, I believe. Actually, I've got it written down here. So, yeah. Zip sheet, and then the BBM equation ut minus ux minus uxt. So this can be done in just two stages. Okay, so I'm going to let x be dominant, x first, and then if there's any t left over, we'll do the t at the end. Okay, a nice bit of cake. for some reason. Okay, and then the variables, the other variables, u is going to be less than ut, is going to be less than ut. There's only one ranking we can do with so few independent variables. Okay, so we're starting in stage 1 with EU x applied to C. And we're calling it C naught because this is the first stage. So we're initializing C naught is C and F is 0 and G is 0. And we're going to say C is Gx F plus Dy so that's at the beginning. Okay, so EU C naught. Now, this identity tells you that what you don't do is evaluate EU C naught. Instead, you use that identity, which tells you that that is the same as dt of ut x to C naught. Okay, this sounds counterintuitive, but actually it's really useful. So if we take the Euler operator with respect to ut, treating u as if it were of no interest because it's a completely separate variable. Okay, but we do the Euler operator with respect to ut, which turns there and there and there. Then what we actually get after a little bit of a sum is u squared. Well, that's very nice. Okay, and now I promised that I could write that as ux or something, and indeed we can. dt of dq. Turns out that eux and dt commute, which is very nice. Okay. So we're going to let C1 be C naught minus what's in here, and that's going to be our G naught is a third U cubed. And we do the sums, and we get 2uxt times the equation now. Let's switch boards. I think I can just about reach that. Well, I don't want to go down too far because I won't be able to get it up again. Thanks very much. That's great. Minus u cubed ux minus u squared ux xt. All right. Now we get to have projected pi u x naught c1. So what that does, every time you see a u or an x derivative of u, set that to 0. So that bit goes, that bit goes, that bit goes, and we're just left with 2u xt. Remember, ut is treated as a completely separate variable from u. Okay, so c1 minus pi u x naught and c1, we know from the theorem is dx of f naught. And then you use your magic formula to integrate and find the f naught, the one that I didn't show you that uses partial scalings. And of course, because it's a unique solution, you can just stare at it and do it by parts. But f naught is, what is it? Minus a quarter u4 minus u squared u xt. Okay, so now you update, Okay, your f becomes f naught. It's 0 at the moment, so f plus f naught. Your g becomes the original g, which is 0, g naught. And your c naught becomes that projected out part that we forgot about, which is 2uxt. ut minus u xxt. You can see where this is going, I hope. Okay, so that's the end of stage 1. Stage 2, that's it. Thank you.
Peter, are you almost converged now, or we are we are
Yeah,
really
I was almost converging. Don't worry. Yeah. So literally almost converging. You're absolutely just coming to it. So yeah, see, we've got u t x c naught is 0, and therefore when you plough through, there's no other terms. That's got an x derivative. C naught is dx f naught, and when you work out what the x and the f naught is, you absolutely get what you're looking for, ut squared minus uxt squared. And that is the minimal representation that I showed you back a few slides ago when we looked at the 13-term one that the standard representation gives you. So this gives minimal representations for lots and lots of equations. When it doesn't give minimal representations, it gives near minimal representations. That is to say, there's not a lot of expressions throughout. It's just because there's a slight freedom in inverting the Euler operator as to what you take. So that's my talk.
Shall we take a quick question here and then the rest of the question in the break? Please. Yes, Kurush.
It's a side question, but does it make sense to talk about quantum Noether's theorem, the quantum for quantum field theories?
Well, when you say quantum Noether's theorem, what do you mean?
Well, for the field theory, which you quantize, you ask for conserved quantities, and you want to understand this from Noether's point of view.
If you've got a set of differential equations, whatever their origin, with Noether's theorem absolutely applies. Yes, there isn't a special quantum. So I thought you might know something that I didn't there on that, but no, there isn't a special quantum one. We're just taking the equations as they're given.
What about systems?
Sorry?
Systems.
Systems. Yes, this all applies to systems. So although the examples I've shown you all scale, non-linear is a good example of a system where you convert it into its real form as a pair of coupled equations. That one has a minimal representation. It has two conservation ones. And so on.
Thank you, Peter. Are we ready for some cake? Yes.